let me start our session about the turbulent flow. Okay, so what do you know about the turbulent? Everyone, I want your participation to explain to me what do you know on your understanding about the turbulent flow. What is turbulent? Have you ever heard about turbulent before? Is the turbulent very important in our daily life? What's the turbulent effect is? Can you explain what is turbulent? What do you know about turbulent effect? Is the turbulent effect in our daily life? Have you seen turbulent in your daily life? Okay, thank you, Naim. So, what mostly you look at the turbulent in your daily life or in your application? Turbulent. Afiq, Rohaizam, uh, turbulent, Eugene, Yong. What do you know about turbulent? Okay, correct. Pipe at sync. That is the, I think the question last night, right? The sinky. So the turbulent flow is where you try to open up your pipe sinky, and then you realize that the water is smooth flow or not flow, not so smooth. Is it a rough flow or smooth flow? Okay, tank at roof house. Okay, anyone? Okay, around the aeroplane get the turbulent ke doktor? Definitely yes, Zara. Around the turbulent, around the aeroplane, specifically the wing, the aeroplane wing got the turbulence surrounded, right? So I would like to show you what is actually Lamina flow. Okay, this is a really good example, the Lamina flow. Alright. This is example of Lamina flow. The flow of Lamina is very smooth. This is the pool. Can you see this? These people, okay, this guy want to create the Lamina flow. This is not Lamina flow. This is actually turbulent flow. Because turbulent, there is a disturbance, kacauan. Okay, this is might be. Okay. This is not Lamina. This is not Lamina flow. So based on this equation, let me find first. The Lamina flow is like the flow is in a static condition. It is like no moving. It is like static. It is a freeze. So I can say that this is one of the example. The flow is very smooth. It is like a static flow. The flow, you won't see any kind of movement in X, Y, and Z direction, right? It is very smooth. So can you see here? Even though there is the flow, but it is look like it is a static. It is no motion at all. It is like a mirror. Right? So however, when we talk about the turbulence, definitely it is on the opposite side. So it is a chaotic mass flow, disorderly flow. Sometimes the turbulent flow come from very high speed, Renault number, or there is the disturbance, kacauan. Alright, so for this study, we're gonna investigate what is actually the turbulent flow in a pipe. So this is the subject matter. Turbulent flow in a pipe is where we apply to a single pipe. That means we have the pipe, we apply to the cross-sectional area, which is circular cross-sectional area. So this is what we call the turbulent flow applied in a single pipe. So in our daily life, most flow in the pipe is the turbulent flow. So it is hardly to see or to view the flow is laminar. It is very difficult. In our daily life, all the flow mostly turbulent flow. That is why you need to learn the effect of turbulent flow, because this turbulent directly affect our daily life. Most of the flow is turbulent flow in the pipe. Alright, it is hard to see the laminar flow. Alright, so you can see here, this is all three velocity component. When we talk about velocity, we have the vector form, which is magnitude and direction. So U, V, and W is the direction in X, Y, and Z direction. U represent the velocity in X direction. You can see that the velocity is fluctuating. It is up, down, many times. So the magnitude also different. So this is what we call as the turbulent. It is chaotic flow. It is not smooth as laminar flow. Alright, so far you guys understand what is actually the turbulent flow? Okay, so now you know that turbulent flow happen in most of the application, right? So this is in terms of V also fluctuating, in terms of Z flow also fluctuating. So all this flow is fluctuating flow, we call as a turbulent flow. So most of the calculation, it is harder to solve in the fluctuating flow, because sometimes at time 2, for example, at time 1, the velocity 2 meter. At time 3, the velocity 10 meter per second. At time 12, the velocity is 100 meter per second. So the velocity is not constant. It is sometimes keep increasing, sometimes keep decreasing. So it is a fluctuating. Alright. So let me draw first in order for you to understand better. Okay. Okay. So for example, this case. Okay. This is sorry. Okay, for example, this is the cross-sectional in the pipe. Sometimes the flow at time equal to 1, it is 5 meter per second. And then at time 2, the flow is 25 meter per second. At time 3, the flow is 35 meter per second. So the flow is fluctuating across the cross-sectional area. Alright? So maybe at 4 seconds, the flow is become 1 meter per second. So it is increasing and decreasing. It is a fluctuating flow. You can see in here. Right? So it is for us, as the engineer, you are the engineer to be, it is very hard to solve the equation, especially when the equation involves the steady flow. Normally, the previous chapter, you make assumption it is steady flow, right? What is steady flow? Anyone? Please comment. What do you know about the steady flow? What is steady? Christopher? What do you know about the steady flow? Yes. Arif Aiman, no change in time. Okay. This is, I give you, we like to play. Okay. Arif, give the solution means that no change in time, steady. Okay. I can give this one lah. This is Arif. Okay, this is Arif. Arif answer. Anyone? I want the accurate. Christopher said d over dt and the system equal to 0. Okay lah, right? Okay. Right. Okay, maybe Christopher almost close. I give like this lah. This is Christopher. Okay. Anyone? What is mean by steady? Amirul, want to try? What mean by the steady flow? Okay, Zara. Steady flow. Okay, Zara like this. Okay. I think Zara mentioned this is about the free flow. This is the free flow, no shear. Zara outside of this target map. Okay, rate change of mass equal to 0. Okay lah, Chen around here lah, this is Chen. Okay, CH. Daus, dB over dt. Okay. Okay lah, this is Daus. This is Daus. Chen, anyone want to try? What mean by the steady flow? Christopher almost close. Okay. What mean by the steady flow? Zara, want to try again? It's okay. So what mean by the steady flow? Okay, correct. So this is Zara. So Zara. So actually, the steady flow means all the property remain the same, constant. All right. There is no change of property. So what mean property? It is velocity, it is density, it is a mass, it is the temperature. All we call as the property won't change with time. All right. So the steady flow mean all the property won't change or constant with respect to time. Okay. So from here, that is why in order to make it steady, we have to divide all the property with respect to time in order to get the average property. So this case, the average property is velocity. In order to get the average velocity, you know that across the cross-sectional area, okay, there might be 100 meter per second. Here might be 20 meter per second. Here might be 1 meter per second. So this velocity is a fluctuating velocity. So in order to make it useful, it is better for us to average them. So we need to average all the velocity happen. Alright. Sometimes when you try to average, you try to plus and divide with 3, right? This is the average. Alright. So why we cannot use this method? Because we have so thousands of different velocity. That is why we need to apply the integration methods. Alright. In the integration, we can integrate from the very small area to become very big area. So that's why the integration is the most important fundamental rule to get the average velocity. So in this case, we apply the average. So this is the flow. The flow is fluctuating flow. This is with respect to you. This is with respect to time. So in order to get average, this is the average. Alright. This we call as U average because this is average for the whole velocity flow. So in order to get the average, we have to divide the whole velocity there with respect to time. So that's why we divide over time. For example, this is from here to here is T, capital T. And then we do the integration from 0 to T for the velocity here, U with respect to T dt. Alright, so far you guys understand what is meant by the average velocity? So far you guys clear? Okay, thank you. So remember that you need to apply the integration of the velocity divide with the time in order to get the average velocity. Why average? Because all the velocity cross the cross-sectional area is fluctuating. It is increasing, decreasing. So it is fluctuating. We need to average. It is easier. So for those learning using the CFD, if you learn CFD, the one that I explained to you before, the application of CFD, like NCs, like IC flow, you will play around like this. So once you know this fundamental, you will apply the Ran's method, Reynolds average Navier-Stokes equation. That one is very interesting. This is very fundamental, right? So this is the reason you need to do the integration in order to get the average. Okay, this average. Okay, you average, and you must know that we have U fluctuating. This U we call as a U dot, U prime. This is U prime refer to the U fluctuating. At the instant of time, this U value is, for example, 100 meter per second. At this instant of time, this U is 70 meter per second. So this we call as the U prime, U fluctuating. And U bar is the average velocity. Alright? This is example. I will explain more in the tutorial. Don't worry. So, why we need the differential equation? Why we need to learn the differential equation? Alright, this is the reason. Alright, differential equation must be solved to provide us with the time average velocity distribution. Alright, so that means that we need to solve the differential equation in order for us to get the time average. So because all the velocity is fluctuating, we need to average them with respect to time. That is why we need to do the differential equation to get the time average. So this can be done by using the particle approach. Alright, it is the same as the elementary approach that we learned previously, but this one we call as a particle. It is the same, the particle approach. What is particle? The particle mean, you can see here, we take only one small portion in that the fluid medium and take it out. Once we take it out, we analyze inside the particle. Alright, once we analyze, we can solve it. So in this case, we take this small portion in the shapes of cylinder. Alright, so from this equation, we know that this is the turbulent flow. It is moving. So it is, when it is moving, we can apply the conservation of, alright, momentum or Newton's second law. So what is the Newton's second law? What is the Newton's second law? Anyone? Yes, F plus ma. Yeah. Okay, this is Newton second law. Okay, apply Newton second law, which is F equal to ma. So from the Newton second law, F equal to ma. So from here, mass, this is dv over dt. So we can say that mass over time is mass flow rate multiplied with velocity. So mass flow rate is actually rho a v multiplied with v. So can you see here, we have rho, we have a, we have v, we have v. Are you clear so far? What is actually the force? F equal to ma, we have the rho, we have the a, we have the v multiplied with v. Okay, yeah? Based on this one. Okay, so why suddenly we have the negative? Because negative here is the x component. Negative here is the x component due to the momentum exchange. Alright, as I mentioned previously, sometimes the flow increasing, sometimes the flow decreasing, sometimes the flow increase. So there is the increasing, there is the decreasing, there is the increasing. So the negative notation, it means they consider as well the negative decreasing flow, which is here. Alright, that's why they put here negative. You can see here negative to consider the decreasing flow. So U mean the flow in the x direction, right? You can see this is the fluctuating. Remember, U prime is the fluctuating flow. It is increasing, it is sometimes decreasing. It is random. Alright? So from here, okay, from here, you divide this with area. Okay, divide this with area. And then you leave, you can cancel out this term, and dF over dA is actually the turbulent shear stress. Alright, this is the symbol of turbulent. dF over dA, which is here negative rho V prime U prime. Okay, so far you guys understand? I want your feedback. Okay, so far you guys understand, yeah? So, since it is a turbulent, it is a chaotic flow. So why not we average the term? So we can put this average. We can put this average. So finally, it leads to this one. So the average, the time average turbulent shear stress is actually equal to negative rho U prime V prime average. Alright? Alright. So in the pipe, as I mentioned before, in the pipe, this is the pipe. This is very long pipe. The flow, this is the normal condition. The flow can, the initial flow can be Lamina flow. And after a quite short time, a long time, maybe a long time, the flow change into turbulent flow. So we have two kind of flow in the pipe, Lamina plus turbulent. That is why the total shear stress, which is tau, is actually the combination of, okay, the shear stress from the Lamina plus the shear stress from the turbulent. Alright, the shear stress from the Lamina is, we learned previously, the shear stress is mu delta U over delta Y. This is, since it is average, we average the velocity. And this shear stress for the turbulent, previously we discovered that, you can see, the shear stress of the turbulent is negative rho U prime V prime average. So from here, okay, from here, you just replace negative rho U prime V prime average. This is tau shear stress. So this is the equation for the total shear stress to consider Lamina and turbulent as well. Right? So this is the first you need to know. Alright. So from this case, I think I will show you the last part. Okay. Okay. Before we end, I want to show you the derivations of the pressure gradient. Okay. So based on this, okay, I want you to focus this. Okay, this is the particle approach where you take out only small portion of the particle in the fluid flow, and then you realize that this particle have the force. We have the force here, we have the force here, and then we have the shear force. Alright, so this force we call as the force here is equal to pressure times area, which is area of the circle pi r squared. This force we call as the force 2 equal to pressure plus the change of pressure, this is bar, multiply with pi r squared, because this is pressure at this point. This is pressure at this point. We have to plus. Okay, the difference is dP. So we have to plus. So this is the force, the shear force, which is tau multiplied with the cross, which is the circumference area. Tau multiplied with 2 pi r dx. This is area. I think yesterday I explained what is 2 pi r dx. Yeah, it is the area of the paper, the rectangular. You try to roll this paper. You try to roll this paper and then you open up. This is actually the area. Okay, so far you guys understand? I explained yesterday. Anyone? Okay, so you can apply, alright? So you can apply the summation of force in x component equal to mass time acceleration. So since this is no accelerating, we consider this one as the average. You can see here dp prime, dp average. So this acceleration is equal to 0. So the summation of force is actually equal to 0. It is under constant velocity, against constant velocity and no acceleration. So what is the force in the x component? Which is pressure pi r squared. And this force pointing to the left, which is negative P plus dP pi r squared. And then this shear force pointing to the left, which is negative tau average 2 pi r dx equal to 0. And then you try to expand this further, you will get the answer is pressure pi r squared minus pressure pi r squared, because negative P multiply with pi r squared, and then this one again negative dP pi r squared, and then this one negative tau average 2 pi r dx equal to 0. Okay, and then you need to divide this whole term with pi r. So this one you will leave, divide with whole this with pi r. So this one we cancel, this will 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 cancel. And you realize that this is the same term. PR minus PR. This can cancel out 0. And then leave only negative dP R. Okay, negative tau average. Okay, 2 dx equal to 0. So you rearrange here, you will get tau, okay, equal to negative wait, yeah. Okay, you will get negative, this is R over 2, okay, dP over dx. So this is average. So can you see it is the same with this one, right? So this one actually we can say that, okay, we can say that this negative R over 2, okay, delta P prime average over L. Okay. Okay, this they consider only magnitude, right? Magnitude only. So far you guys understand, yeah? I explain how to derive until it form the final form. Alright, so far you guys clear on this? Okay, nice.